Okay, welcome back. This is the third part of our lectures on density functional theory. Let's look at where we are. In the first part, we looked at the Hohenberg-Kohn theorems, which established one-to-one mapping between the density and the Hamiltonian, and hence we argued that, actually they argued, that the energy could be written as a functional of the density, except we didn't know how to do that. Okay, then we looked at E. Bright-Wilson's observation, which showed how, given a density, you could reconstruct the Hamiltonian by integrating the density to find the number of electrons, and by finding the nuclear cusps. These are the Kato cusps, which would give you the locations of the nuclei and also their nuclear charges. And from this information, you could reconstruct the entire Hamiltonian. So the density did indeed sort of map onto the Hamiltonian, and then obviously you could solve the Hamiltonian in principle to get the ground state wave function and energies, and in fact any of the excited states too. So you may sometimes hear that Kohn-Sham theory or density functional theory is a ground state theory. This is false. You can get information about all the excited states from the ground state density. Okay, in fact, in principle, although I need to think about this some more, you probably could get the same from an excited state density too, but I do need to think about this some more. Right, then we looked at one of the kind of early examples. This is now 1927, when Thomas and Fermi construct an early example of a true density functional. This is an approximate theory. We saw how this functional could be defined, and indeed it is a density functional, and but it's approximate. Yeah. So what Kohn and Sham have done is to say, Hohenberg and Kohn have done is to say that it doesn't have to be approximate. There is, in principle, an exact mapping possible, although we don't know what it is. Now we are on to the major part of this lecture, which is we're going to head to Kohn-Sham density functional theory, which is what we use all the time. But before going there are a few things we need to get under our kind of mathematical cap. First, so let's start here. Now I am still on the lecture notes, which is electronic structure density functional theory 1, and the title of these slides are the electron cusp and density functional theory. Let me start with the just make sure the recording is going on. Yes, it is. Let's start with these slides in presentation mode. Here we are. So you do need to understand functional calculus, right? So functional derivatives, I'm going to assume you have understood it. Now the main mathematical ideas we're going to be needing here is definition of functional derivative, given here, the product rule, given here, and the chain rule. These three things. Now I have already prepared the screencast on useful results, and I can show you what those are. So useful results, Control Tab. Here we are. I have gone through these handwritten, sometimes a little untidy, but I hope you get the idea, handwritten notes on how we use functional differentiation. For more systematic kind of treatment, please see Appendix B in Carsten Ullrich's time-dependent density functional theory book, which you should have access to through the library. Now, the main results we're going to be using here are the following. One is that when we define this tilde density as a sum over chi I star chi I, the functional derivative of rho tilde with respect to chi I star x is given by chi I x delta of x prime minus x. Now strictly there should be a prime here, but because of this Dirac delta, it doesn't really matter. Alright, that's the first of the results. The second one was that the functional derivative of the Coulomb energy, J of rho tilde, with respect to chi I star x, was given by, and this takes a while to get there, was given by the Coulomb potential Vj(R) times chi I x, and the Coulomb potential is the potential that arises from the density rho. It's defined through this integral here. We had one more result, which was that the functional derivative of the non-interacting kinetic energy, Ts, written as the sum of individual kinetic energies, exactly the way we did it in Hartree-Fock theory. The functional derivative of Ts with respect to chi k, I've chosen the k here this time, star, is given by minus a half Laplacian chi kx. Okay, so we're going to be using these results often. I'm not going to repeat the derivations for these functional differentiations, but we will see a few more which might help along the way. So let's get back to those lecture notes now. Here we are. Presentation mode, please. Okay. Now, before going to density functional theory, I want to show you how Hartree-Fock theory, which is what we've been kind of working on for some weeks now, this can be cast as a density functional theory. And now here's how it can be done. The Hartree-Fock energy, as you know, is the minimum energy when we of the Hamiltonian. Now I'm writing the Hamiltonian in the kind of density functional form, where we have a kinetic energy part, an electron part, and this external potential, so which is the electron nuclear part. I've called it the external potential in the second line here. Now it's the minimum of the matrix element of a single determinant with this Hamiltonian and a single determinant. Yeah, so basically with Hartree-Fock theory, what we did was we optimized, we found out what this matrix element was. We then optimized that energy and found the lowest energy, and that gave us a Hartree-Fock energy. So in the language of the constraint search method, which we looked at of density functional theory, what we're doing is we're optimizing or finding the minimum over all Slater determinants. That's what the SD stands for here, or single determinants, which correspond to n electrons. So we're searching through the n electron space of antisymmetric single determinants. Okay, nothing else. That's our Hartree-Fock ground state. Okay, now when we do that minimization, we end up with the Fock operator, which you've seen. It consists of a one electron part, an electron nuclear part, which would be our external potential in the language of density functional theory, and then we have this Hartree-Fock potential, which is the effective potential between which the electrons see. Now we know what that contains. This Hartree-Fock potential contains a Coulomb part and an exchange part. So the entire Fock operator then can be written as a kinetic energy part, an external part, which is of course just the electron nuclear potential, the Coulomb part, and the exchange part. There is no correlation here by definition, because you know we've defined correlation to be whatever is beyond Hartree-Fock. Of course, if this was one electron problem, it would be exact. Right, now what I want to postulate, and then we will show, is that we can write the Hartree-Fock ground state energy as a functional of the density as follows. We can write the Hartree-Fock energy as a functional of rho, and this functional is defined to have a kinetic energy part Ts, a Coulomb part J, an exchange part Ex Hartree-Fock, and then the external potential, that is the electron nuclear potential, contributes to the energy in this form. The integral of rho times the external potential integrated over all space. Now, just to remind you, this last term arises because the external potential is a one electron multiplicative potential, and in the useful results, right at the start of useful results, I showed how this comes about. So this is quite an important result, so please make sure you have understood it and can show this in general. Now, what are these terms? How are they defined? The kinetic energy itself is simply the sum of the one electron kinetic energy terms, as we had in Hartree-Fock theory. In fact, of course, this is going to give us Hartree-Fock theory. The Coulomb energy, now where did I define that? Over here, yes. The Coulomb energy is defined as the standard Coulomb energy of the self Coulomb interaction energy of the electronic density, rho. I'll come back to the slide in a minute, and the Hartree-Fock exchange energy is written in terms of this double sum over these exchange integrals. Now once again, you've seen all this stuff. I'll look at these terms a little bit more detail, but this functional should not be surprising. Effectively it is a statement of the Hartree-Fock energy in a single determinant. But what I'm going to try and do is show you that Kohn-Sham density functional theory is formally exactly the same. So let's just complete the mathematical picture and show that if we optimize this functional with respect to changes in the density, then this leads to the Fock equations. Alright, that's our goal here. Okay, I had some comments here. Now I made these things some while ago. Let's see. Yeah, so this bit in blue here just deals with some of the mathematical subtleties of stating that you can write down such a functional in the first place, because I mean it comes, I don't want to spend too much time on it, but what we want here is to write this thing as a functional of the density. Nevertheless, even in the very first term we've written down here, this is not a functional of the density. This is a functional of these spin orbitals, chi-i's, and the same applies to the exchange term. It's only the Coulomb term and this external potential term which are actually written as functionals of the density. The other terms are explicitly written in terms of orbitals. So if you are going to optimize with respect to the density, is it even possible? Or do we need to optimize with respect to the orbitals? And what we're going to see is that we actually do need to optimize with respect to the orbitals. It's not the density. Hartree-Fock theory is not a density functional theory. And in the same way, I would argue that Kohn-Sham theory is not a density functional theory. But let's get into this at the end of these lectures. Alright, so for now we're going to treat this as a kind of density functional theory and see where it goes. Alright, now the very first thing we want to do is to modify this Coulomb energy functional a little bit. Now, what we've written down here follows from standard definition of the Coulomb energy of a charge density rho. Just to give you a motivation, in case you've forgotten your electromagnetic theory, if you have a charge density in space, then take a little bit of charge density at point R1, a little volume there, and then you take another little volume at point R2. Those two volumes are separated by distance R12, and they interact through the standard Coulomb's law, Q1 times Q2 divided by R. That gives you the energy between these two. Now, of course, those are two little volumes, so you want to integrate over all space twice for R1, then for R2, to find the total energy of the system. That gives you the double integral, and you need the half because, of course, when you perform this double integral, you will find the energy of rho R1 on this side with rho R2 on that side, but also the other way around. You'll double count it, so we need the half there. Alright, so that's where the Coulomb energy comes from. And if you look at your Hartree-Fock derivation, then the Coulomb energy there is exactly in this form. Right, so why do I then need to change from a rho to a rho tilde? Well, what we're going to end up doing is performing a functional derivative with respect to chi-i star. Now, rho itself is written as the sum over I goes from 1 to n of phi I star phi I, where the phi I is the spatial part of the spin orbital chi-i. There is no spin there. So it becomes inconvenient, and I've explained this in the useful results notes, so please have a look at this again. It becomes inconvenient to work with the rhos directly. Instead, we will work with rho tilde of x, where x, just to remind you, is a composite coordinate. It contains r and the spin coordinate, so the spatial and spin coordinate in there. So rho tilde x, which is defined as the sum I goes from 1 to n of chi-i star x, chi-i x. And if we integrate over spin, so I perform an integral over d omega, then we get the density rho. Alright, so all we need to do to get from rho tilde to rho is perform the spin integral. And the best way for you to see it is, take the 1 electron case and see that you get this. Okay. I may also refer to rho tilde as the density. Now, some of these notes were written a while ago when I was working just with rho and not rho tilde, and so some of this terminology might have, but by density, by density I would mean either rho tilde or rho. You can get from one to the other quite easily. Rather, you can get from rho tilde to rho quite easily. Now, what about the exchange functional? Well, the exchange functional is also written in terms of this rho tilde, and or rather more explicitly, it's in terms of the chi's, not the rho tilde. Yeah, you should recognize this from Hartree-Fock theory. Again, you have a minus a half, double sum, double integral over x1 and x2, and then you have chi I star x1, chi j star x2, and then we have this permutation operator p12, which exchanges the electronic labels on the right. So it operates on the right, as all operators conventionally do. So p12 would interchange x2 and x1. Okay, and this is where the term exchange in fact comes from. And just to remind you that these sums go over the occupied states only. So if we believe that this functional here is a density functional, and I hope I've given you some reason to doubt that this is a real density functional, but if you believe it is a density functional, then what we are doing then is writing Hartree-Fock theory as in this way. We have this density, Hartree-Fock density functional here for the given rho tilde in it, and we minimize over all possible rho tildes that arise from a single determinant with n electrons. So we've got to search the space of all possible densities which arise from a single determinant with n electrons, and this would give us the minimum, and that minimum would be the Hartree-Fock energy. Now, formally, the density is a rho tilde is a function of the composite coordinate x. So it has 3 spatial coordinates and 1 spin coordinate in it. That's 4 dimensions. If I give you a 4-dimensional function, any 4-dimensional function, can you guarantee that it does correspond to a single determinant with n electrons? Okay, the n electrons part is easy. Integrate rho tilde over all coordinates, you should get n. If you don't get n, it doesn't correspond. What about a single determinant? How do we know we're going to get a single determinant? I mean, that it arises from a single determinant. This is not easy. In fact, this is very, very hard to prove. I don't even know if the proof exists for this theory. So what we're going to do is do what is often done in this field is although we write things formally as a density functional, really what we're going to do is optimize the orbitals in that theory. So we are really working with a determinant, not with a density. And in this way, I feel like Kohn-Sham density functional theory, by calling it a density functional theory, we are really kind of stretching the definition of a density functional. Alright, so here's what we're going to do. Let's forget about this being a density functional. We know it is a functional of the orbitals chi i's, and we know what each of these terms looks like. Now let's optimize it with respect to those orbitals. So I want to optimize this energy, the Hartree-Fock energy functional, subject to some constraints. I want to put in constraints that these orbitals are orthonormal. And we put in these constraints like we did in the derivation of the Fock operators through Lagrange multipliers. And we'll choose our Lagrange multipliers to be these epsilon ij's, and I've chosen the sign to be a negative sign because I kind of know where it's heading. Okay? So these are the undetermined Lagrange multipliers coming in with a negative sign. And I think PLR has a nice section on how the method of Lagrange multipliers works in one of the appendices. So if you want to look this over again, look at PLR's book in one of the appendices. This functional is called this omega functional. So omega is a functional of rho, or frankly at this point I'm going to pretend let's just call it a functional of the orbitals, and it's the Hartree-Fock functional. Take away these constraints. What we want to do is to optimize it. Optimizing it, let me just look ahead if I've written this down somewhere. I haven't. Okay, what we want to do is to take the functional derivative, that's this thing here, of the omega functional down here. So I want to take a delta omega with respect to chi I star x and set that to 0. That's what we are after. Now in order to do this, we need to, of course, differentiate each term under this expression here. Now I have already done this for most of the terms that appear in this functional, and these derivations are the ones I showed you over here. So you do need to look this up, you do need to follow these derivations carefully, and you will end up with the results I'm going to show you now. Alright, so let's get on with this again. We're going to be using the chain rule, and we've seen how it's done there. We're going to use the chain rule repeatedly, in fact. I'm not going to go over this now, but this is typically how it works. We take the functional derivative of one of these terms, in this case it's Coulomb energy with respect to chi I star x, and use the chain rule, and simply work off systematically each of these functional derivatives that appears in here, and you'll end up with a straightforward result at the end. In this particular case, we get, as I've shown you in detail in the useful results notes, the Coulomb potential times spin orbital chi I x. Now here's where you get your big question, because what I want you to show is that when you perform this systematically on all terms in this with respect to chi I star, set that functional derivative delta omega by delta chi I star to 0, you will end up with the Fock equations in their non-canonical form. So we still have this sum over all the spin orbitals on this side, and you have to apply a unitary transformation on this epsilon matrix to diagonalize it to get the Fock operator equations in the canonical form. We have done this in the Hartree-Fock lectures. I won't do it again here. You can find out more about this in PLR's book and in Szabo and Osland, where it's described in some detail. Okay, so in this way, 1 second, I just have a pause here if you don't mind. Alright, we're back on now. Let's get this started again. Presentation. Right. So this is, okay, so where are we now? Okay, so that's Hartree-Fock theory. We have seen rather quickly, but we have seen that you can write the Hartree-Fock functional in a certain way. It appears to be a density functional, but when you look into it in a little more detail, it's actually a functional of the orbitals. Nevertheless, you can write it down as a functional. Let's have a look at it again. There it is. Optimize it with respect to changes in each of the spin orbitals, and you get the Fock equations. Okay, now how do we... But that's an approximate theory. Remember, Hartree-Fock theory is intrinsically approximate except for one electron systems. Now that wouldn't do any good. I mean, there's no point writing a density functional theory like that. What we need is to find a way to write the functional exactly. So here's what Kohn and Sham did. Well, we can write down, this is our functional of the density. This shouldn't have rho tildes in it. Actually, that's fine. Yeah. By using rho tildes, remember, is the density before we integrate out the spin. So let's just remind ourselves as to what rho tilde was. Here it is. Rho tilde of x is equal to the sum I goes from 1 to n of chi I star x chi I. It's not a density. To get a density, you have to integrate rho tilde with respect to the spin coordinate. Alright, so here we have then is this energy is a functional of rho tilde. We have a kinetic energy part, an electron part, and the external potential part. This is exact. However, we don't know this, and we don't know this. So what do we do? Now, we did see Thomas Fermi theory gave us an expression for T, but it was approximate. Thomas Fermi theory can also give us approximations for the electron-electron part, but it's also approximate. So what do we do? Now, what Kohn and Sham did in '65 was to say, let's postulate the existence of a non-interacting system in an external potential Vs. This is much like the Hartree-Fock potential, except it's a different external potential. It's not the Hartree-Fock one. And this system is such, it's a non-interacting system, which means there is no electron-electron operator. Instead, we have quasi-particles. We're going to call them electrons, but they're not really electrons, because electrons interact with other electrons. These particles don't. These quasi-particles, these Kohn-Sham electrons, if you wish, they exist in this kind of a Hamiltonian, kinetic energy part and this effective potential. And the property of this system is that it yields the exact density. So you solve the system, you find the lowest energy solution, and you will get the exact density from there. Brilliant. Okay? So what's the use of that? Well, when you solve this, this is like a Fock equation, but these are going to be the Kohn-Sham equations. You will end up with a set of orbitals and orbital energies. These will be our Kohn-Sham orbitals and orbital energies. Now, let's work backwards. So if you know you're going to get orbitals, well, you can write down what that kinetic energy functional should look like. It should look like this. This is simply the kinetic energy of each of the orbitals, summed over all orbitals. Okay? This is the non-interacting kinetic energy of this system. Exactly the way we had it for Hartree-Fock theory, but this is not going to be the Hartree-Fock kinetic energy, because these orbitals will not be the Hartree-Fock orbitals. They will come out from this Hamiltonian, which is going to be a Kohn-Sham Hamiltonian. Alright, so we know what Ts is. Now Ts is not the exact kinetic energy. That's fine. Now this was our unknown Kohn-Sham functional, F, which is written exactly as the sum of the kinetic energy part and the electron-electron part. Now the kinetic energy part, we are going to write it as, the majority of it is going to be Ts, that's Ts. The electron-electron part, well, we know it contains a Coulomb interaction, which is this double integral over rho times rho divided by R12. And then we have the rest, what we're going to call exchange and correlation. So we know that the rest contains exchange because we know that this electron-electron part, besides the Coulomb part, it contains an exchange part. But it also contains correlation, and there's also some correlation contribution to this kinetic energy. That's all bundled in here. So this is the exchange correlation functional, EXC of rho, which we don't know what it is. We know parts of it, we don't know the whole. We'll define it formally as a difference. So EXC of rho is this term here. These two terms take away these two terms. So it's the exact kinetic energy minus the single particle kinetic energy minus the exact electron-electron energy minus the Coulomb energy. That's a formal definition. Let's live with that for now. Alright, so now we can write down our Kohn-Sham functional, energy functional, E, as the single particle kinetic energy plus the Coulomb energy plus this unknown exchange correlation energy plus the external, the energy from the external potential with this density. Let's compare it to the Hartree-Fock functional. For Hartree-Fock we had a single particle kinetic energy, Coulomb energy, a Hartree-Fock exchange functional, and the external, the energy from the external function. I just wrote this the other way around, but it's the same as that. So what's the difference? Well, the only difference is here formally. This one contains exchange and correlation effects. This one contains only exchange effects. I'll just make a pause here and then we can resume. Yes, just wanted to check if it was recording. Alright, so is there a difference between these two theories? Well, not formally. I mean, they contain very similar elements. In fact, even when we derive the Kohn-Sham equations, we're going to do exactly the same as what we did to derive the Fock equations from here. We're going to vary this thing, sorry, the Fock equations from here. We're going to vary the Kohn-Sham energy functional with respect to the orbitals chi I star. Alright, let's proceed. Well, we don't know what this is, but can we go ahead and see what we can end up with? So here's our Kohn-Sham functional to be minimized subject to the orthonormality constraints here, that these spin orbitals are orthonormal. And as usual, we put them in using Lagrange multipliers. As before, it's going to be Lagrange multipliers of the form minus double sum over I and j, epsilon ij, and these are our orthonormality constraints in there. Now, let me just look ahead a little bit and then we'll come back here. Yes. So what we're going to show then is that if we optimize this so that the functional derivative of omega with respect to a chi I star is set to 0, then we will end up with the Kohn-Sham equations, which is what we wanted. But we will also know what this potential is. This potential will be defined to be the sum of a Coulomb part, an external part, and an exchange correlation part. Now, if this sounds familiar, yes, it is exactly what we had for the Fock equation a few slides ago. The Coulomb part will be defined to be arising from the integral of rho tilde of x prime divided by r minus r prime dx prime, and if we perform the integral over spin, so the d omega part, then we can convert the rho tilde into a rho, so that's also written as the density rho divided by r minus r prime dr prime. The external potential is simply the electron nuclear potential, which is the sum over all the nuclei z alpha over modulus of r minus r alpha. Remember, r alpha are the locations of the nuclei. It's an attractive potential, hence the minus sign. Now the exchange correlation potential, well, to know that, we need to know what Ex is. Now at the moment we don't know what Ex is, it's the unknown, so we'll simply write it formally as the exchange correlation potential is the functional derivative of Exe with respect to rho tilde. Now I have put this equivalence here because this is when you perform this functional derivative, you formally get something that's a function of x and not spatial coordinates only. There'll be spin coordinate also there formally, but because of the way we are going to define Exe, there will be no spin coordinate, and hence it's also written equivalently as a regular potential in terms of r only. Now let's see how these potentials arise. Alright, so once again we're going to have to differentiate the omega functional with respect to not the density but the spin orbitals. So we need to have d by d chi I star x. To perform something like this, we need the chain rule because some of the quantities in this omega functional are written in terms of the density. So the chain rule says you take the integral of an auxiliary coordinate dx prime, d by d rho tilde x prime, d rho tilde x prime divided by d chi I star x. Alright, so this x corresponds to this x, and this coordinate here and here correspond to the auxiliary coordinate here. The last term in here, which we'll see quite often, the variation of rho tilde with respect to chi I star, is given simply by chi I x delta. This is the Dirac delta of x prime minus x. Now we've seen this before. It's also, I've shown you how this arises in the useful results tutorial, so please have a look at that. Before we go any further, I just want to show you something. This definition for the density is correct for a single determinant. Now, in general, the exact theory will not be a single determinant theory. In fact, there is very good reason to believe that Kohn-Sham theory, like Hartree-Fock theory, should be a multi-reference theory, and you've already seen this for the H2 dissociation case. As you pull the bond, the two hydrogen atoms apart, we need more than one determinant to correctly describe the dissociated state. So in a multi-determinant theory, rho tilde is written as the sum over the basis functions of chi I star chi I as here, but now we have this fi's here, and these are called occupation numbers. They need not be integers. So here you might say that we have occupation number 1 or 0. It's 1 if I is between 1 and n points included, and it's 0 if I is greater than n. While in the multi-reference theory, multi-determinant theory, these fi's occupation numbers could be between 0 and 1, and the only constraint is that they sum up to n because there are n electrons in the system. But we won't go into this anymore. I just wanted to point it out here. Alright, so as I've said, we've already shown that the functional derivative of J with respect to chi I star is the Coulomb potential Vj times chi I x. Let's see it again. Functional derivative of J with respect to chi I star x. Use the chain rule. Now I have used 3 primes here because I know what's going to come in next. So we have an integral over an auxiliary coordinate x triple prime dj by d rho tilde x triple prime d rho tilde x triple prime by d chi I star x. That's simply a statement of the chain rule. We know what this last term is. It's here. Chi I x, the Dirac delta function x triple prime minus x. Okay, so that's the last term gotten rid of. We'll leave it there. Now we need dj by d rho tilde. That's d by d rho tilde of this double integral in here. Okay, now either use the formal definition of the functional derivative or the sloppy physicist definition, but you need to be able to show that the functional derivative of this thing is the half goes away, and you can see why the half is going to go away, because this behaves like a rho squared. D by d rho squared would give you a 2 rho, and that's where the 2 goes in. And each time you perform a functional differentiation, you drop one integral. So one of the integrals from here goes away. That leaves you with 1 and the one outside. And then we have rho tilde x prime divided by r triple prime minus r double prime, chi I x from here, and the delta function from here. And then this delta function collapses one more integral to give us a single integral over dx prime rho tilde x prime divided by r minus r prime times chi I x, which is the Coulomb potential times chi I x. Now I realize that this might look a little obscure. The only way for you to see, convince yourself that it makes sense, is for you to apply these techniques for yourself clearly and systematically. So please do that. And also please look at Carsten's book and my web screencast on useful results, because these steps are explained there in a little more detail. Alright, now what about, let's take another one. So this is now the external functional, which is given by the external potential times rho tilde integrated over dx. Well, the functional derivative of ext by chi I star, once again the chain rule. We know what this last part is. It's chi I times delta function, and we know what this part is. Let's apply the quick physicist way of differentiating this. You treat rho tilde as if it was a variable, a standard variable, differentiate this with respect to rho tilde, drop one integral sign, and that's what you get. Oh yes, and you have to change the variable in here, which is r, to a primed variable because of the denominator has a prime in it. And then this delta function drops the remaining integral to give you the external potential times chi I. If this looks a little complicated, once again just go back and apply the definition of a functional derivative. Okay. If you have any still further doubts on this, I will perhaps put up an even more detailed explanation as to how these things are done. Finally, the last thing which we can do is this Coulomb is the exchange correlation potential. As I said, we can't really define it because we don't know what EXC is, so we define it formally as just the functional derivative of EXC, and that's it. That's where we stop. Okay. That lets us put everything together. So this Kohn-Sham potential then is a Coulomb potential, an external potential, and this exchange correlation potential. And this is what they look like. We know these first two terms, we don't know the form of the last term. Once you know the potential, you can solve the Kohn-Sham equations, like we solved the Hartree-Fock equations. So the Kohn-Sham operator operating on chi I, which is kinetic energy, is external. This effective Kohn-Sham potential operating on chi I gives us epsilon I chi I. And you got the energies, like the way, so you get the orbitals and the energies exactly the way we have the Hartree-Fock orbitals and energies. These equations also need to be solved self-consistently, like we solved the Fock equations, because, for example, the Coulomb potential contains the density, and the density is made up of these solutions chi I. So you need to make a guess for this before you can start to solve these equations to get chi I. And then you improve the guess iteratively until it converges. Alright, so that lets us write down the Kohn-Sham energy as a kinetic energy part, a Coulomb part, an unknown exchange correlation part, and the part with the external potential. Now this is all written in terms of this density rho tilde, which is before the spin integration. Once we've got the form of the Kohn-Sham energy, we can then perform the spin integration to write it in more conventional form in terms of the density itself. And that's the form we're going to use from now on. A little bit of manipulation. The way we when we looked at the Hartree-Fock equations, at some point we also looked at the sum of the Hartree-Fock orbital energies and showed that it was not equal to the Hartree-Fock energy. Well, we could try the same thing here. The sum of the Kohn-Sham orbital energies is given by the matrix element of the Kohn-Sham single determinant with the sum of the Kohn-Sham operators and then a single determinant. So that's the matrix element of psi naught with the Kohn-Sham operators. We have put it down here in their full form, the kinetic energy part and this effective part, the effective one electron potential part, Kohn-Sham determinant. This can be written as a kinetic energy part plus a part where we have all the effective one electron potentials in there. This first part gives us the Kohn-Sham kinetic energy functional, and then from here we end up with the matrix element of the Coulomb operator, the external potential, the Coulomb potential, the external potential, and the exchange correlation potential. Now I am skipping a few steps here, and I probably should have made a few more detailed lecture notes here, but I hope you can see that this is a one electron operator. So we apply our result, our general result. Let's have a look at it. Somewhere here, it's the beginning of the useful results section. If you have a one electron operator and you have the matrix element with a single determinant, an n electron wave function, which includes a single determinant as a special case, n electron wave function, one electron operator, n electron wave function, that matrix element is written as the integral of the density times the one electron operator integrated over all space. So we're using the same result here. The last term gives us the integral of ρxc times the density integrated over all space. The second last term gives us the external potential, density integrated over all space, and the first term would give us something similar, but you could also write it, and I want you to do this. So you would normally get the integral of the Coulomb potential, density integrated over all space, but this can also be written as twice the Coulomb energy J. I want you to understand why we get a 2. You need to figure this out. Alright, so then we can write down the kinetic energy as equal to the sum of the orbital energies minus twice the Coulomb energy minus the external energy minus the exchange correlation energy, and that lets us write the ground state energy then as the orbital energy sum minus the Coulomb energy plus the exchange correlation energy minus Vxc times rho. Now this is not a mistake. Just looking at it, I thought it was a mistake, but it isn't a mistake. The external potential energies cancel off with this term over here. Okay, so this is just an alternative way of writing down the Kohn-Sham energies, the Kohn-Sham energy of the ground state. Right. So what have we done so far? Because we're nearly at the end of what I want to show you here. We have seen that Hartree-Fock theory can be cast as a kind of density functional, but one that was intrinsically approximate, right? We have seen that Kohn and Sham proposed this effective model where you propose the existence of a non-interacting system of Kohn-Sham electrons which interacted in this one electron potential Vs, and this system had this amazing property that the ground state density of this system was the same as the ground state density of the exact system. And using that auxiliary system, we could write down the energy of this Kohn-Sham. We can write down the exact energy as a sum of a kinetic energy part, a Coulomb part, an unknown exchange correlation part, and this part arising from the external potential, which is the electron nuclear potential. Now, if I took this exchange correlation part and replaced it with the Hartree-Fock exchange part, this would give us the Hartree-Fock energy as the minimum. So clearly, if we're going to go beyond Hartree-Fock, we really need to know what's in this exchange correlation part. And if you can find a good approximation to the exchange correlation energy functional, something that is better than the exchange functional in Hartree-Fock theory, then we would be in business. Then we would have a theory which was formally the same cost as Hartree-Fock, but it would be better than Hartree-Fock. We would be getting beyond it. We would be recovering the correlation in ways in which we could not in Hartree-Fock by definition. So how do we do it? Yeah, in what Kohn and Sham have done effectively is to take all the unknowns and put it into this one thing. Now that's fine, because we know all this other stuff. We just don't know what this thing is. Now they've taken a bigger problem. The big problem was we didn't know what this energy functional was in the first place, and we've converted it into a smaller problem. Now we are after one piece of this. We've put together all the other big pieces. We just need this one more piece. That's where we're heading now. How do we find approximations to the exchange correlation energy functional? Okay, so that's what I've just said, I think. This is a question which I've asked you before. It's, if V is a one electron spin-free operator, then the matrix element of single determinant with V is the density times V. Now please prove it for yourself. But what we now want to do is to look at possible approximations for this exchange correlation energy. I'm not going to go into great many details here. We will look at more in the next set of lectures. But in brief, what Kohn and Sham did was to extend on the ideas from Thomas Fermi theory. So they say that the exchange correlation energy is written as the integral of the density times some exchange correlation density, epsilon xc. And epsilon xc itself is a function or functional of the density, and possibly the gradient of the density, Laplacian. You could go on. Now, traditionally what's been done is epsilon xc has been split into an exchange part, epsilon x, and a correlation part. And what follows is now finding approximations for these two parts. One of the earliest approximations, this was the one which was actually provided by Kohn and Sham in their 1965 paper, was called the local density approximation. And there's a picture of how this works on the next slide, I believe. Oh, yes, it's coming up. Now, in the local density approximation, you can write down the exchange correlation energy as the integral over rho times this exchange correlation energy density. Now, this exchange correlation energy density in the LDA, local density approximation, is simply a function of rho. In fact, it turns out to be a homogeneous function of rho, where the exchange part is taken to be what's called the Slater functional, and we'll see how this is derived. Slater functional is given as minus a constant times rho to the 1/3. Now, if you stare at this for a while, you should realize you've seen it before. When we looked at Thomas Fermi-Dirac theory, we looked at the Dirac exchange functional. It's exactly this one, with the density multiplying it. So this is what the energy functional for the exchange part is. It's minus a constant, which is the constant Cx we've seen before, times the integral of rho to the 4/3 r dr. That's it. It is a density functional. This is indeed a density functional. Now, what about the correlation parts? Well, the correlation parts are more complicated. If you want to see what they look like, look at Carsten Ullrich's book, where he shows you some of the correlation parts we use when we specify the LDA or functionals like blip. There are two common choices. So what was done for the LDA was that you can fit the density to various quantum Monte Carlo calculations of the correlation energy for the homogeneous free electron gas at different densities. This is a fit which has been done, and you can do it in a few ways, and people either use the Perdue-Wang parameterization or the Wosko-Wilk-Nusser parameterization. There are small differences in these two, and some functionals use one and some the other. But they are all part of the LDA. Now, pictorially, this is a figure from the book A Chemist's Guide to Density Functional Theory by Koch and Holthausen. Pictorially, what the LDA is the following. If you look at a non-homogeneous electronic density, in this case it looks like the density of water with some funny swirls in it, and you look at a little bit, it's non-homogeneous, it varies in space. But if you look at a little volume of it, rho r1, this little volume over here, well, it is approximately homogeneous, and it has a density rho r1. You look a little bit away, and you get another density rho r2. It's kind of approximately homogeneous in here, but it has different density. So for each of these, you take a different exchange correlation energy density, epsilon xc, and then you integrate over all possibilities, and this gives you the LDA. So at each point in space, we're using a different exchange correlation energy density, and that, when integrated over all space, gives you the LDA. So, in other words, a molecular density or an inhomogeneous density consists of little bits of density which are homogeneous, and put all together, you can, this is one way of putting forward an approximation. Right, so you can generalize the LDA. In fact, it was done in 65 paper to a local spin density approximation. Here's where you split the exchange correlation energy density into two parts, one for the spin up, one for the spin down. It has, by the way, the LDA is already better than Hartree-Fock, and the energetics are poor in general, but it's better than Hartree-Fock. Putting in spin densities let you work in for cases where you had open shell systems, you had magnetism involved. It was much more general than the LDA. You could get beyond the LDA by including density gradient information in this energy density. So now epsilon xc depends on rho and the gradient of rho. This is called, in a particular form, this is called generalized gradient approximation, or GGA, generalized gradient approximations. There's a whole class of GGAs. There are many functionals. So if you just say I used the GGA, it's meaningless. You've got to say which GGA you used. And as with the LDA, the GGAs split the exchange correlation energy density into an exchange part, a correlation part. They differ from the LDA through this enhancement factor fx. So the first part here, rho times epsilon x LDA, looks like the LDA, but then we have this extra function f of x, which is a function of s, and s is the reduced density gradient. It's dimensionless, and I've got a question here. How do you show it's dimensionless? This is a nice exercise. It's defined as the modulus of the density of the gradient of the density divided by rho to the 4th hertz and some constants. Right. Here are some forms of what those enhancement factors look like for common functionals. This is the Becky 1988 functional. It has a single parameter in it in this functional. Becky fitted this parameter on a bunch of exchange energies for rare gas atoms. He chose this particular form because it was known to obey certain exact relations. Now, the story of density functional theory in the 90s, I guess 80s and 90s, was a story of finding exact relations. The more you understood that these functionals should satisfy certain exact relations, the more you could build those relations into your functionals. And so Perdue, Burke, and Erzenhoff, this was the classic paper where these three guys built in, I think, pretty much all the exact relations known at the time into this this form, and they had one parameter which was not fitted to any particular data but was obtained by requiring certain limits to be obeyed by this functional. Most physicists use the PBE functional, Perdue, Burke, Erzenhoff. It is by and large one of the workhorses of our field. It has consistently proven to be reliable across the board. When other functionals fitted to particular kinds of systems might fail, this one doesn't. There are failures in all these functionals. In general, we'll come to these, but this is one I would highly recommend. All right. I think we will stop here, and actually, let's go on. We're coming nearly to the end of this lecture, but my voice is flagging. Here's a question which you should have if you had some time to stop and think at this point. Well, let's think about it. In Hartree-Fock theory, we know what the exchange functional should be. Alright, so let's have a look at it. Somewhere up here. In Hartree-Fock theory, we know that the exchange functional takes this form. And we know it's pretty good. So why not use that exchange functional in Kohn-Sham theory? You know, why go to this later exchange functional, which is much simpler for sure. Look at this. I mean, this is just rho to the 4th hertz integral. That's it. There's no orbitals in there. But the Hartree-Fock, the Hartree-Fock functional, for many ways, and we'll see this later again, has got very good properties. So why not construct an exchange correlation model which has Hartree-Fock exchange, and you take only the correlation part from your density functional theory. It turns out that this theory is better than Hartree-Fock, but it's much worse than the generalized gradient approximations. And it took a while for people to figure out what was going on here. And the reason was cancellation of errors. You see, the Hartree-Fock exchange functional in a way is exact. The correlation functionals from density functional theory are not. Now, when you used something like the Slater exchange functional, this one here, you made a kind of error. But when you paired that with one of these correlation functionals, part of the error ended up cancelling out. When you paired it, on the other hand, with a Hartree-Fock functional, well, nothing cancelled out. So you suddenly had a near perfect exchange functional, but now all the sins of the correlation functional were laid bare, and this theory did not work. Okay, but this was, people were now already starting to think about the right sort of thing. Can we use a bit of Hartree-Fock over here? And in 1993, Becky proposed one of the first so-called hybrid functionals, where he said, well, let's take a certain fraction of the Hartree-Fock exchange, not the whole thing, just a fraction, and we'll take the remaining fraction, 1 minus a, of the standard generalized gradient approximation exchange, and then the whole of the correlation. Later that year, he made a slight modification, and Stevens and others also modified things. And essentially what they did was to combine the Slater exchange, the Hartree-Fock exchange, the Bina 88 exchange, and a couple of correlation functionals in a way in which you got pretty small errors on a whole range of systems. And this is called the B3 lip functional. It's one of the workhorses of computational chemistry. Probably 95% of calculations done by chemists use this functional. In my opinion, as a physicist, a much better choice is the PBE functional, PBE0. Now, PBE0 is based on PBE, but it contains 25% Hartree-Fock exchange. So here the B3 lip functional ends up having 20% of Hartree-Fock exchange. PBE0 functional has 25%. Otherwise, it's a simpler functional, and it can be quasi-derived on theoretical grounds, but it's only quasi-derived. So, can we understand why these hybrid functionals should exist? And there's quite a simple way. Let's have a look at our Kohn-Sham and Hartree-Fock energy functionals. On the first line here, we've got the Kohn-Sham energy functional, and then we have the Hartree-Fock energy functional. Let's take a linear combination of these two. Let's define a hybrid functional to be 1 minus x of the Kohn-Sham part and x of the Hartree-Fock part. Add them together, you get something that looks identical to the Kohn-Sham part or the Hartree-Fock part, but now we have 1 minus x of the exchange correlation from the density functional and x times the exchange part from the Hartree-Fock. Now if you compare this to what Becky has done, it's identical. And in a way, what he's done is simply combine pieces of these two functionals, and you get a hybrid functional. Now this is not the only way you can make a combination of these. You can combine them a little more intelligently, and what you get then are what are called range separated functionals, but that's for another lecture. Okay, so these days we have a whole slew of density functionals, and John Perdue, one of the granddaddies of the field, has put together this biblical picture of Jacob's ladder. Now I haven't drawn a ladder here, but he actually has a ladder going up on the left hand side. So at the bottom you have inaccurate hell, and you have the LDA, local density approximation, and the LSD, the local spin density approximation, which depend only on the density rho. On the next rung of the ladder you have the generalized gradient approximations, GGAs, which depend on rho and the gradient of rho. An example is PBE. On the next rung we have what are called meta GGAs. These depend on rho, the gradient of rho, the Laplacian, and the kinetic energy density, which is defined through this expression here, where each of these is kinetic energy of an orbital. An example of this is the TPSS functional. Now frankly I've never used them, but they are supposed to be an improvement over PBE. You go to the next rung, you get what are called the hyper GGAs, of which things called range separation functionals exist, and we'll come to this in the next lecture. Examples here are CAM B3 lip, and these fix problems with each rung is trying to fix a problem with the lower rung. So here something called the charge transfer problem is fixed. Then we have the correlation hyper GGAs, which include correlation missing in the rung below. And then we reach chemical heaven, or if you're a physicist heaven, I don't know. Right. So I'm going to leave you with one question though, which we have discussed. This has come up during this lecture. is Kohn-Sham theory a density functional theory? We wrote down these energy functionals as functionals of the density. But then we wrote down, when we actually put down the forms of these terms, we wrote them explicitly in terms of orbitals. The kinetic energy was written in terms of orbitals. The Coulomb part was written in terms of densities. The exchange correlation part, we will see, is also written in terms of orbitals quite often. And so, is it fair to call this, and then if you go into a hybrid functional, the Hartree-Fock exchange part is in terms of orbitals. So is it a density functional? Now Thomas-Fermi theory is a density functional theory, but modern Kohn-Sham theory, I would argue, is not. And perhaps you should correctly call it just Kohn-Sham density functional theory, or KS-DFT. Just to differentiate it from the theory we might have one day, which might be a proper DFT, density functional theory. But I would say at the moment we are firmly in the realm of orbital density functional theories. With that, let's stop here, and we'll continue with more an analysis. So what we need to get to now is just how well do these density functional theories perform, where do they fail, how do we fix them, and what's on the horizon. That's where we're heading next. Alright, finished.